everyone. I'm Deepak, and in my lab at CMU, our long-term goal is to build agents that can generalize to lots of tasks in lots of environment. Okay? So we are really after this general purpose embodied intelligence. So what does that mean? It's lots of agents doing lots of tasks in lots of these environments. But this is very far from the way things are done today. Oops, sorry. In reinforcement learning or in general deep learning. Like we have systems that can do one thing really, really well, but they're barely able to generalize beyond what they are trained for. Okay, like for instance, something that can play at the game of Go can barely pick up object on the table. Now, this problem is not specific to reinforcement learning or deep learning. This is generally there in all of machine learning. Like let's take this example of supervised learning, the most simplest case of machine learning. An example of this ImageNet challenge, where we have models which can achieve superhuman accuracy on ImageNet test set, like over 80%, these models. Let's see what happens if I take these models and test on the real world. A video from YouTube, not very far. This is ResNet 50, and it finds things like cobra snake, ray fish, flatworm. Right? So the model that achieved superhuman accuracy on the training set completely fails to generalize when tested on any sort of real data. And the reason is not very surprising, because in machine learning, whenever we start any machine learning course, the first assumption we make is that data at training time, at test time, they come from same distribution. And whenever that does not happen in practice, things do not work. And the scenario is worse in robotics, where I can have a very expensive system that can perform lots of things in the training set, but it's difficult to generalize to a very simple task of putting a block on a table, which can do pilot tricks on the left, right? And every failure in robotics can cost you thousands of dollars, unlike classifying an image wrong in ImageNet. Okay? So the real question is, how do we generalize beyond training? And my philosophy is, I think what is currently wrong with the way we do things today is as follows. We train a model, we keep it frozen, and then we test at deployment. Like we do not change the model at all. This is kind of saying like keep your brain frozen and then function in the real world. Like if your brain was frozen after the age of 10, no matter how smart you were by the age of 10, you cannot really function in the world. The real world functions in a very different way. Like our basic principles of generalization rely on being able to adapt continually over time. But how do we formulate this adaptation? Now there are many works in the lab which focus on this, and to get into more depth and limited time, I'll focus on only one work which of this flavor of this adaptation. So let's say you have a single task, and the task is to walk. Now you train this agent in simulation to walk in certain scenarios, and now your goal is to test this agent in new environments, in new unseen scenarios, out of distribution per se. So how do we achieve this generalization at test time? Now the key idea in our approach is that we allow the robot to adapt at test time, and not just directly deploy the trained model. So before I go to the approach, let's see some results from this. Okay, so here this robot was trained in simulation, and now from simulation we directly put this in the real world and test it on very different scenarios. So here is this robot next to a riverbed. The reason it is able to generalize from very simple terrain in simulation to this complex scenario because it is adapting at test time. Now this robot is blind, has no vision. So if it gets stuck, it uses its leg to get around the obstacles. You also test on stairs. Note it was never trained on stairs. It's just taking the robot and putting on stairs directly. And the reason it is able to work here is it is adapting in real time. And I'll show you how in a moment. There is one more scenario. This terrain is deformable. Now it's very hard to even simulate such a terrain in simulation. So we cannot even train even if you wanted to in these scenarios. One more example of vegetation. One more example, like something inside the house with many planks. And then as the robot moves, the plank moves. These are kind of disturbances which are very hard to create intentionally in simulation. There is one more example where the robot is walking on unstable ground or walking on the beach. And in these it's hard because the robot has very thin legs. They get stuck in mud. We can avoid those things at test time directly. Now, let's look at how did we train this robot and how does it adapt in real time, because this adaptation is happening in fraction of a second. So I'll quickly go over the approach. So this approach is called rapid proto adaptation, and we showed this on legged robot. The idea is more general than robotics per se. Okay? So let's go through the method very quickly. So here is a outline. So this robot was trained in simulation. As I said before, it is trained by reinforcement learning. Now, it's very common in reinforcement learning when you train a robot in simulation or any system is to randomize the domain and find an invariant solution. Now, in contrast to that, we do randomize the domain, but instead of finding invariant solution, we find conditioned solution. So we condition this policy in simulation with some privileged information that only we have access to in simulation, and we train this policy with that encoding. So we take this privileged data like mass, center of mass, friction. We encode this into some latent space, and then you pass this through a policy to output the actions. This is very basic, nothing interesting so far. But the key thing to note here, this policy is adaptive. It's not invariant. It's not robust. Like, it is not going to find a same solution across all scenarios. It will find a solution conditioned on the current setting of the environment. Okay? But this is a good side. The bad side is I cannot deploy this policy anymore because I don't have these extrinsics in the real world. Like, I don't have this in the real world, like neither the mass, center of mass, friction, height, and all this, right? So the key idea here is that we want to estimate this signal in the real world by some other information. So in particular, what we do is we estimate these extrinsic vector, which is of the privileged information, from history of the robot. Now you can say, okay, why is history important to tell me about the properties of friction? So it's not. But it is important to tell you about the effect of friction. So think of it this way. When you move your hand in the air or in the water, like you have to apply more force to move your hand in the water. And that force tells you, that extra force tells you there is something out there which is restricting your movement. So the discrepancy of what you apply action to the robot and how it behaves, that discrepancy has the signal to tell you how to adapt to that scenario. So we train this in simulation with this adaptation module, which we call RMA. The training is really simple. Like in the phase 1, you perform simple reinforcement learning with privileged data. Then in phase 2, you perform supervised learning. So you regress the parameters from the, like you have base policy, you copy it in the phase 2, and then this module is trained to regress to the latent space from the history of the information. Okay? So reinforcement learning, supervised learning. So second phase is really efficient. Now once you have trained this, you take the base policy and module and you put them together to find this answer. Now you can adapt this, this latent vector Z in real time on any new setting at a very high frequency. Okay? Now let's look at this, how effective this module is in practice. I already showed some results, but let's analyze it in more detail. So here is an analysis. So here we ran out of difficult scenarios in the real world outside. So we went inside home again and made this difficult scenario where we put oil onto the ground. Like in academia, usually we are not very rich, but the student used olive oil, so which was I was not very happy about. But then we put plastic on the leg of the robot as well, so that it slips even further. And then we asked it to walk over this way. It's really hard to appreciate how difficult this is. So let's see it again in slow motion. It's slow down. So you can see that the robot is almost about to fall, but it can still move forward and do things in this environment. Right? And one more example, the robot is walking and we throw a 5 kg weight onto the robot. This is again a hard task because 5 kg robot is not 5 pounds, 5 kg. So if I tried this in the lab, when our student was walking and threw a 5 kg weight on his hand, and it was really hard to catch online. And you can see here in slow motion, the robot at test time is adapting very naturally like an animal-like motion. It bends its legs to account for the inertia. You cannot train for these things because this cannot be done in simulation directly. And actually you can also analyze this module very carefully, like multiple dimensions of this module, and you can see the adaptation happening in real time inside the network. So these are 2 dimensions, no PCA, no TC, the actual dimension, and they change the behavior. And we show this in many scenarios in the paper. And you can also do it with adaptation or without adaptation. So if you have this 8 kg payload, the robot itself is 12 kg, very light, and the company says their limit is 6 kg. We put 8 kg, which is already out of company's limit. And on the very top, if you see RMA, it can walk just fine. But if you did not have adaptation, just watch out for the second video and try to hear the sound. So it walks. It's a very hard fall, and so we had to do this experiment to convince everyone that, okay, this is actually working. One more scenario, mattress. Now mattress is, you cannot simulate it, it's deformable. If you adapt, you are fine. But if you don't adapt, you just fall after some time. And we have also compared them to control approaches, which are regular in locomotion community. And those approaches cannot function on mattress at all, because in mattress, there is no force feedback. So your controller, which are hand-coded, completely go haywire. So the robot jumps out of the mattress as if it thinks it's in an elevator or in the air or something. Okay? Anyway, so there are a lot of work in locomotion for the last several decades, not just years. So what makes this approach exciting? What makes it exciting to me personally, the idea assumes nothing about a robot. This assumes nothing about the motor, nothing about joints. It starts completely from learning, completely from scratch. So there is no hand-coded or heuristic control stack anywhere in the robot. All we use is PID, two-line code from control, and nothing else from the last 50 years of control literature. We use nothing. We start from learning all the way. And then we show generalization to out-of-distribution scenarios. The slides are somewhat weird. The third point is that this architecture is asynchronous. So this robot costs $2,700, very cheap, like 20x cheaper than Boston Dynamics, and it can achieve all these good results with low-cost motors. But one thing to focus here is that we do not hard-code any gate or any structure in the robot. This is important to me personally, because I'm a big fan of things emerging on their own and hard-coding as less as possible. But here, very good behaviors emerged on the robot, but they did not show such nice gates on flat terrain. Like animals show all these nice gates, like dogs, elephant, horses. You take any quadruped, they have very nice gates. But those gates were not present in here. So we wondered, okay, why is it just why are the gates not emerging? So we went back in biomechanics and found this paper which says that animals evolution may have baked in the structure of gates in animals and they may be trying to conserve energy. And they did this experiment in 80s on horses, which shows that at low speed they walk, then they trot, then they gallop, because these gates are efficient at that speed. Inspired by this, we just add one more term in the optimization, which is energy function. Try to also conserve energy while walking. And when we do that, magically, these gates emerge at different speeds. So at low speed, our robot walks. At medium speed, it trots, and then it gallops. So here is an example. So it's like in the low speed, you see the bottom right, it's walking. As you increase the speed, it trots. If you lower down, again walks. If you again increase the speed, it will again now gallop. And these gates are very similar to those of animals. We have analyzed the pattern over there as well. And here is an example of gallop. It's an important gate. It's like cheetah is running, all the legs in the air. And we discovered a flight phase, which is really difficult to hard-code and control. Like the whole heavy robot in the air from beginning. So this is difficult to get to. And then when you make a plot of this robot, and it looks like the plot from Hoyt and Taylor from 1980s. With one catch, we did not account for electrical energy of the battery, which they did because they measured oxygen of the horse, oxygen consumption of the horse. In more recent updates, we have also added vision onto this robot. It was blind so far, but now it can avoid obstacles. This paper is on archive, just a couple of weeks back. It can avoid obstacles, very robust, can walk over any terrain, can throw weight on top of it. Obstacles can also be transparent. It can detect the obstacle from its own body by hitting it and then updating its own map. The person opened the gate, but not fully. It was transparent, so it can go around and avoid obstacles. Okay? But this was so far same task, diverse environments. Like same task, diverse environment. But there is more to intelligence. Like we also want to discover new tasks. I'll not go into this, but briefly mention. This is another main line of work in our lab, which is inspired from psychology, because learning multiple tasks in practice is very hard for reinforcement learning because they rely on reward. Like in these games, all these AI agents, they rely on reward or reward shaping. And these rewards are really hard to get in the real world. Like this apple here, like apples are given in the maze to guide the agent, but there are no apples in the real world. In the real world, the reward could be delayed by days, months, or years. So how do humans get around this problem? Well, psychologists argue that humans rely on intrinsic motivation, curiosity to go around this. And we have been building, working on this for last 5 years, trying out different formulations of curiosity, and we have achieved, this is slightly buggy. Yeah, so we have applied the idea of curiosity-driven learning across many scenarios, as you can see here, from different robots to games, etc. And I highly recommend you to check this out. Okay, so I believe in the long term, agents have to function both in same task, diverse environment, as well as the same environment and diverse task. And these things, okay, it stopped going next. Can you do next on the slides? Okay, I'll just speak over, so I'm almost near the end. Okay, I believe in the long term, what we need is these two things to function together, like both generation to new tasks and new environments. And towards this long-term goal our lab is building towards, there are also several other missing pieces which we want to fill gaps with. Like for instance, like when we grow in natural world, it's not just our software grows over time, our hardware also grows over time. So we are working on how to evolve hardware and software together in robots. Like real world is very dynamic also. Like when you write on whiteboard, writing on whiteboard is a very dynamic task. You move your hand very smoothly, etc. So we are also building systems that can write on whiteboard with very smooth dynamic systems. Like you cannot see the video, but there was supposed to be a video here. It's again stuck. I wanted to just have the last video play somehow, because that's, yeah, so robots in the wild. This is a very recent result. We haven't published it, just a video I wanted to show. So here we are able to apply all these principles in a same pipeline, and we put a mobile manipulator, which can move around and has, if you can just play the last video, that would be great. So we put that robot in the wild, and this robot solves thousands, not thousands so far, but hundreds of tasks in lots of environment. So we have this robot, which is arm and a base. We take this robot to every kitchen in the CMU, because it snows a lot in Pittsburgh, and we took it to every kitchen. It tries to solve every task in every kitchen. And all it needs as supervision is just one video of a human doing it, and not telling the robot how to do it, just doing it on their own. And if that video plays, watch out for the paper. Let's see. Next. Let's ignore this also. This is not important, but we can control robots with just bare hands. You may have seen Jeff Bezos a couple of years ago wearing very large gloves on his hand to control these robots. We don't need gloves, no rig, just iPhone camera, and we can control directly from a video. But this is the most exciting part for me. Like all this research is culminating just now to this system where we have this robot performing lots of tasks in lots of environments from just a single video supervision. With that, thank you.